Hi everyone, this is Dr. Sandeep, Associate Professor in the Department of Mechanical Engineering, working in Institute of Aeronautical Engineering, Hyderabad. So today's topic is about interatomic bonding in solids. So what is the main objective of studying this interatomic bonding in solids is, if you want to know the properties of the material, or if you want to characterize the material, or if you want to know the characteristics of any material, one need to know what type of bonding is the material is having, whether it is a chemical bond, covalent bond, ionic bond, or metallic bond. So depending upon these types of bondings, one can characterize or one can analyze the properties of the materials which are useful in different applications. Now we'll see what is the interatomic bonding between the materials and what are the different types of interatomic bonding between the materials. Now, what is the reason, what is the importance of studying this interatomic bonding is, if you want to know the properties, different mechanical as well as physical properties of any material, any solid material, one need to know the importance of the bonding between the two atoms. Okay, so this interatomic bonding allows us to explain the characteristics of the given material. And therefore, we have different types of bonding. We have primary bonding and secondary bonding. So in primary bonding, again, the primary bonding has three different categories. That is covalent bond, ionic bond, and metallic bond. Coming to the secondary bonding, we have dipolar covalent bonding, interpolar dipole compound bond. So the main difference between these two bonding is that in primary bonding we have a higher values of bonding between the atoms. When you compare with the secondary, they have very less strength. That's why most of the atoms which have primary bonding are useful in mechanical applications. So now we'll see what are the different types of bonding in each type of category. So here three different types of primary or chemical bonds are found in solids. So what are those? Those are covalent, ionic, and metallic bond. Now, for each type of bonding, how we are categorizing? How we are categorizing whether it is covalent bond or ionic bond or metallic bond, depending upon the type of bonding between the atoms, whether it is directly contacting to each other or indirectly contacting to each other, and how it is being contacted or how it is being attracted towards each other. It differentiates the type of bond. So the secondary bonding are very less in strength, and also it has very less melting point. So these secondary bonding type of elements or materials are not used in huge applications. Mainly in the mechanical stream of applications, the secondary type of bonding are not that much useful for our applications. So now we'll see what are the different kinds of primary covalent bonding are there. Now in the primary interatomic bonding, first category is about ionic bonding. Ionic bonding. So this ionic bonding is very easy for us to see physically also. By physically also, we can identify the type of bonding in ionic nature. So what is the main thing is happening in the ionic bonding is the positive and negative charges, when they're coming too close to each other, what is happening? There is an attractive force between the atoms. So because of this attractive force between the atoms, what is happening? The bond between the two atoms is very strong. So what is happening? By visually also you can see the interaction between the positive and negative. Both are coming to each other and giving a good type of bonding. So it is always found in compounds that are composed of both metallic as well as non-metallic elements. So this type of ionic bonding we can see in metallic and non-metallic elements also. So what are those elements? So these metallic and non-metallic elements are situated at the extreme, horizontal extremes of the periodic table. So here you have metallic and here you have non-metallic. So these both metals in the periodic table, which are at horizontal extremities in the periodic table, will have the type of ionic bonding. So what is happening? The atoms, whatever the atoms are there in this ionic bonding. So the metallic element will easily give their valence electrons to the non-metallic atoms. Okay, whatever the atoms which are having in metallics, so they'll easily give their valence electrons to the non-metallic atoms. So in this process, what is happening? In this process, the atoms acquire a stable of inert gases, stability. Okay, it happens a stable nature. So because of that stable nature, what is happening? There is strong between the elements. So because of the process of the metallic element is giving valence electron to the non-metallic element. So here you are getting a strong bonding between the elements, and you are getting an additional electric charge to the element, whatever the element you are using. So best example to explain this ionic bonding is the sodium chloride. Okay, sodium chloride is the classic example to explain about the ionic bonding. So what is happening in the sodium chloride? So if you see, what are the if you see in this figure, the sodium and chloride. Okay, so here you can see the positive symbol and negative symbol. So because wherever there is a positive and negative or both opposite poles, what is happening? There is a good attraction between the molecules or the atoms. So because of the strong bonding between the elements in this ionic bond, since the positive ion is attracted towards the negative ion, so this is called as a Coulombic force of attraction. So what is Coulombic force of attraction? There is a strong attraction between the molecules which are in opposite in nature, opposite in electric charge. So here the sodium chloride is forming by the help of the compounding Coulombic bonding between the atoms. So because of the positive and negative charges are attracted to each other, you are getting a good bonding between the elements. So wherever you can see, so either in this direction, vertically. So wherever you see, you can see the positive and negative. So wherever horizontally or vertically, you can see all the positive and negative charges. So because of these charges, positive and negative charges, there is strong attractive force between the molecules in order to get a good bonding element. So this is the schematic representation of ionic bonding in sodium chloride. So there is a good attractive force that is called as a Coulombic force. Why you are getting that Coulombic force? Because there is a positive and negative charges between the ions and of the electric charges. Because of the electric charges, there is a strong attractive force on each other. Thus, the sodium chloride ions are being formed. So this is about the ionic bonding. So next category in the primary bonding is the covalent bonding. So what is the covalent bonding? So this is again in a covalent bond, we have stable electronic configurations are being assumed by sharing of electrons between the adjacent atoms. So here what is happening? Sharing of electrons is being happening by adjacent atoms. When the adjacent atoms are being shared with another atom, there is a attractive force between the elements, and this type of bonding is called as a covalent bond. Here we are getting a stable electronic configuration. So see, in any type of bonding, we need to have a stability. Okay, if it is not a stable condition, what is happening? We are not getting a good type of bonding. So always remember that there should be a stable configuration, stability in the bonding. Then only you will get a good type of bonding. Otherwise, if the bonding is not stable, what happens? There is a weak forces are being acting on the atoms. So you won't get that much strong bonding between the elements. So in order to have a good bonding, strong bonding, there should be a stable condition. So that's why in this covalent bond also we have stable electronic configurations. So these are to be assumed. How means? By sharing of electrons between the adjacent atoms. So that's why what is happening here? Two atoms that are covalently bond with each other contribute at least one electron to the bonding. So what are the adjacent atoms are being sharing electrons? So here what happens? Two atoms. What are the two atoms that are being covalently bond to each other? These are trying to share these are trying to contribute at least one electron from that bond. So what is happening here? So this atom again attract to another atom to form a good bond between the atoms. So what is happening? Now from these two atoms which are covalently bond, at least one atom is being shared to the other bond, so that the shared electron is being considered to belong to the both atoms. So both the atoms, these two atoms are being shared. So if you want to explain clearly about this covalent bonding, what is happening? Methane, CH4, this is the best example where how the carbon is being shared with the hydrogen, we'll see. So in generally, what is happening in this methane, carbon has 4 valence electrons. Do not. Carbon is having 4 valence electrons, whereas hydrogen has single valence electron. So in this methane, what is happening? Carbon is having 4 valence electrons. And how these 4 valence electrons are being shared to the hydrogen, we will see now. And how it is being formed a covalent bond by sharing these 4 valence electrons with the existing single valence electron in the hydrogen. Now you can see clearly in this picture what is happening. So this is the carbon. Okay, this is the carbon, and here you are having 4. 1, 2, 3, and 4. So these are the 4 carbon components, atoms. And here what is happening? This carbon is sharing with the hydrogen. So this is the hydrogen. And what is happening in the covalent bond? It has to share with the adjacent. So this is the adjacent for the carbon. So carbon is sharing its electrons to the adjacent of the hydrogen. So that's why you can see in this figure. So initially the carbon is having 4. Okay, 4 valence electrons. Initially we have 4 valence electrons for the carbon atom. And how many valence electrons you have for the hydrogen? You have a single valence electron for the hydrogen. Okay, now this carbon, whatever the carbon is having 4 valence electrons, now it is being shared with the hydrogen to form a methane. How it is being forming methane, carbon and hydrogen? Because of the interatomic distance is very, very less, and it is strong between these two elements to form a methane compound. So now this carbon is being sharing with the hydrogen. Okay, so how many you are getting here? Total 8. 2 plus 2 plus 2 plus 2. Total how many? 8. So here what is happening? Each hydrogen atom is acquiring a helium electronic configuration. Because it is being sharing with the carbon, so each hydrogen atom is being acquiring a helium configuration to have a stability in the configuration. So here when the carbon atoms are being shared with one electron, what is happening here? Totally additionally again you are getting 4. So here you have 1, 2, 3, 4. Initially it is being sharing with carbon. Now since the carbon is also having additional 4 electrons are being shared, so totally you are getting total 8 electrons from each hydrogen. Okay, so total 8 valence electrons are being adding in this covalent bond to get a methane compound. So like this, the interatomic bonding is happening between the adjacent elements. So adjacent atoms like this, we are getting adjacently, it is being bonding to each other. So this type of bonding, where adjacent type of bonding between the elements is being formed, that type of bonding is called as a covalent bond. So since in the earlier we have carbon is having 4. So now these 4 again is being bonding with the hydrogen element. So additionally we are getting 4. So 4 plus 4. So totally you are getting 8 valence electrons which are being bonding between the methane compound. So the covalent bond is directional, and that is specific atoms are being existing only in the direction where between the atom and another participant which are being shading with the electrons. So this is the one of the type of bonding in primary bonding. So what are the different types of elements or what are the different types of materials which are having this compound covalent bond are like you have in non-metallic elements H2, Cl2, F2. These are some of the categories where you can find the covalent bonding in non-metallic elements, as well as the molecules which are containing dissimilar atoms. Also, the atoms which are having dissimilar atoms like CH4, H2O, HNO3 and HF. These are also some of the types of covalent bonding in non-metallic elements. And further, this type of bonding is found in elemental solids. So what type of element solids we can find covalent bonding are examples of diamond, you have silica, germanium and other types of solids which are composed of elements that are located at the right hand side of the periodic table. Like gallium, you can have silicon carbide. So these are the solid elements where you can find the covalent bonding. If you want to find out the non-metallic elements where you can find the covalent bonding, then you can go with the CH4 or H2O, HNO3 or HF. These are some of the molecules or the materials where you can find the covalent bonding. If you want to find out the covalent bonding in a solid structure, like carbon, you can have silicon, you can have germanium. So these are some of the examples where you can find the covalent bonding. And coming to the last category, in the primary bonding. In primary bonding, what we are discussing? We are discussing about the three types, that is ionic bonding, covalent bonding and metallic bonding. So this is the third one, last one in the primary bonding. So metallic bonding. So what is metallic bonding? So there should be free flow of electrons, whether it is a positive or negative. Okay, so metallic bonding can be found in our daily lives. Whatever the automobile you have, whatever the bicycle you have, even the spoons which we are using for dining. So all these are in metallic bonding. There is a free flow of electrons. So because of the free flow of the electrons, what is happening? There is a strong bonding between the atoms. Since there is a easy path of atoms freely, so because of that, wherever there is a gap, this free flow of electrons will fill that gap by attracting the atoms with each other, so that you can have a good metallic bonding between them. So metallic bonding is the final primary bonding type. That is the last category. So these you can easily find, mostly you can find in the metals and their alloys. Only in the metals and their alloys this type of metallic bonding can be found. So what is happening in metallic bonding? So metallic bonding, in metallic bonding, the metallic materials have 1, 2 or more, more 3 valence electrons. It can have 1, 2 or 3 valence electrons. So these valence electrons will share with another atoms. But when you compare with the ionic or covalent bonding, what is happening? Only 1 valence electrons you are having, in whether it is ionic bonding or covalent bonding. But in case of metallic bonding, it can have 1, 2 or 3 valence electrons, and these 3 valence electrons can share with the another atom. That's why, since there is a free flow of passage of these electrons, it can be shared with the another, whether it is 1 or 2 or 3, so that it can form a strong metallic bonding between the elements. And this metallic bonding can be observed in metals as well as at its alloys. So what is happening in this? So since the metallic materials are having 1, 2 or 3 valence electrons, with this model, these valence electrons are not bound to any particular atom. That's what. It is not bound. Since it is a free flow, there is a free flow, that's why it is not bound to some particular atom. Wherever the atom is having some gaps, so at that gap, it will flow easily and fill that gap. That's why it is not bound to a particular atom. And they may be thought of belonging to the metals as a whole, or forming a sea of electrons. Sea of electrons means a bunch of electrons or an electron cloud. So you can see the figure where you can observe what is that free of electrons and how they are being passing. So this is the metallic bonding example. So wherever you find these gaps, this is the sea of valence electrons. So they can easily pass since you have a gap. So wherever there is a gap or not stable, so in this gap, the ions are being passed. What are the valence electrons are there? It can be 1, 2 or 3. So these valence electrons will flow in these sea of valence electrons, and wherever you have the gap, that gap is filled, and there you can observe a strong bonding between the elements. Okay, so most of the cases this type of metallic bonding are being observed in metals and its alloys only. Okay, since you have a free flow of electrons, since there is a free flow of electrons, there is a huge stability in the electrons or huge stability in the material, so that you can form a good bonding wherever the gaps are being filled. Now the free electrons, what are the free electrons are there? These free electrons shield the positive charged ion cores, and from that mutually they will repulsive force of attraction is there. So since positive and negative, okay, so these wherever the free electrons you are seeing, these are having a positive charge in nature, and because of that, what is happening? There is a force of attraction between the molecules, and you are forming a good type of bonding. And it is and additionally, these electrons, these free electrons, what are the free electrons we are seeing in the schematic figure? These act as a glue. That means they will stick to each other. They'll act as a glue to hold the ions core together. So whatever the free electrons which are being passing in the metallic elements, so these act as a glue. This is very useful to hold the core of the element in order to get a good strong bonding. So this is about the metallic bonding. Now if you see the energies, bonding energies and the melting temperatures for the various different types of materials. So here you have the three categories. When you compare with the primary, only you have the primary. You have first one is ionic, second is covalent, and third one is metallic. Okay, these three are the primary bonding types. If you see the ionic compounds, you have NaCl, MgO. Okay, so these are having, if you compare the bonding energy, how much you have having? NaCl is having 640 kilojoules per mole, and if you go with the MgO, magnesium oxide, you have 1000 kilojoules per mole of bonding energy. That means it is very strong when you compare with the NaCl. MgO is having very strong bonding energy. Again, if you go with the melting temperature, and again this should be very high. Here you are having 2800 degrees centigrade. So that means when you heat an element of MgO up to 2800 degrees centigrade, it won't melt. After reaching the 2800 degrees centigrade, then it starts melting. That means it can resist, the material can resist up to 2800 degrees centigrade. So if any application where you are having a high amount of heat is being supplied to the material, that material has to withstand up to 2500 degrees centigrade. Then you can go with this magnesium oxide. You can't go with the NaCl material. Why? Because it is having very less, 800 degrees centigrade. So if you want to have a good resisting material which is having above than 2500 degrees centigrade, then you have to go with the magnesium oxide. Now similarly, the second category is what? Covalent. If you see the covalent example, we have Si and diamond, silicon and diamond. So in this case, silicon is having 450 kilojoules per mole and diamond is having 713 kilojoules per mole. So this is the bonding energy. So here when you compare the silicon and diamond, you have diamond has having a strong bonding energy. And when you compare the melting temperature, what is the melting temperature of Si silica? It is 1410. So it is very less. But when you compare the diamond, diamond is having higher value, 3550 degrees, and that means it is having more than MgO. So that compared to ionic bonding, the covalent bonding materials are having higher rate of melting temperature. Now in the similar way, if you see the metallic bonding, the last category in the primary bonding, you have Hg, Al, Fe and W. Now if you see all these things, the bonding energy is being increasing like this: 68, 324, 406 and 849. And if you see the melting temperature here also, Mercury is having very less, it is minus 39. Aluminum is having 660, Fe is having 1538, and W is having 3410. So now, if we compare all the three primary bondings, now if we compare from this table, if we compare all the three primary bondings, which element is having a good bonding energy and which is having a good melting point temperature. So, how can you justify, how can you decide these are having so and so values? Means if you know the atomic bonding between the elements, then only you can know these values. That's why before going to any application or before going to any selection of material, you have to know all these characteristics. That's what in the starting I told, if you want to know the characteristics of the material or if you want to know the properties of the material, one need to study the bonding, atomic bonding between the elements and what type of bonding it is, whether it is a primary or secondary. Again, coming to primary, what type of bondings you have, whether it is a covalent bond, ionic bond or metallic bond. In some cases, covalent bond elements are good for so its application. And in some other category, yes, metallic bond is having good strength, good hardness value, good bonding energy, good melting points. So these are all we can decide by knowing the properties, and before that you have to know what is the type of atomic bonding between the elements. So this is about the interatomic bonding in solids with primary interatomic. Next, coming the second category is what? Secondary bonding or van der Waals bonding. So now you compare, when you compare the secondary bonding with the primary, you have very less type of bonding between the elements. Again, why? How you are deciding this secondary is having very less? Because the bonding energies are very less in this secondary bonding when you compare with the primary. So that's why you should not select the materials which are having a second category, secondary bonding. Okay, so the secondary, or it is called as a van der Waals bonding or physical bond. So these are very weak when you compare with the primary bonding. And why? Because this is in the range of very less values from 10 kilojoules. So it is approximately around 10 kilojoules. But in the primary bonding, we are having higher values, more than 700, 800 kilojoules per mole we have. But in this case, approximately near values are only about 10. Very rare elements will have more than 10, but approximately all the elements in the secondary type of bonding will have a 10 kilojoules per mole. So the secondary bonding exists between the virtually of all the atoms or molecules, but the presence may be obscured. Why? Because though in every element the secondary bonding is being observed, but it is being absorbed. Why? Means the primary bonding nature is very high. Because of the existence of the primary bonding, the secondary bonding is being neglected since it is having very less values. So that's why though in some materials both primary as well as secondary bonding is available, but the primary bonding is being taken and the secondary bonding is being neglected because of the less bonding energy values. So what is mainly happening in the secondary bonding means it is the evidence for the inert gases. So generally inert gases are very stable in nature. Okay, so which have stable electron structure. What are the inert gases we have? Those are stable in structure, and in addition between the molecules and the intermolecular distance there is a covalent bonding. That's why though it is a secondary type of bonding, the primary bonding is also available. But since they have very less values of bonding energy, these secondary bondings are being neglected. And mainly what are the causes? How the secondary bonding is being formed is because of the dipoles between the elements. That means dipole means what? The distance between the two atoms is very large. If the distance between the atoms is very large, what is happening? The force of attraction is very less. That means the bonding between the elements is very less, so that's why it is very weak. That is why you are getting less bonding energy values in the secondary. So because of this dipolic nature in the secondary bonding, there is a weakness in the bonding energy. That's why the elements which are having the secondary bonding are being neglected and only the primary bonding is being taken into consideration. So, because of this dipolar between the atoms, what is happening? The bonding results from the Coulombic attraction. What is Coulombic again? Between the positive and negative, there is a strong force of attraction. This Coulombic attraction between the atoms is very, very less. That's why there is no strong bond. Now, if you see this example, so here you have a gap, a lot of gap between the atoms or molecules. So, because of the dipolic nature, there is a huge difference. That is why there is a less bonding energy between the elements. Though you have a negative and positive, they have to attract to each other, but since there is a huge gap, that's why there is no attraction between them. There is an attraction, but very less attraction. There is very less bonding between the elements. That's why it is very, very weak. So dipole interaction occurs between the induced poles and between the induced poles and the polar molecules. Between the induced poles as well as the polar molecules which have a permanent dipole. And what is happening in hydrogen bonding, a special type of secondary bonding is found to exist between the molecules that have hydrogen as one of the constituents. So mainly the dipole moment, dipole attraction or dipole interaction occurs in the hydrogen bonding because some of the molecules have the hydrogen as one of the main constituents. So these bonding mechanisms we'll discuss now. What are the things that you're having in the dipole? So first one is the fluctuating induced dipole bonds. So in the name itself you can find out fluctuating. If the electron is not in the stable nature, if it is continuously fluctuating, what is happening? The bond between these two elements will not having good bonding between them. So this is fluctuating and this is trying to getting bond with each other. Somewhere you'll get here bond. Exactly you won't get the strong bond since this is being fluctuating. So what is happening? So since though it is being attracted but is not bonding exactly to each other. It is not bonding exactly to each other, one or the other. So because of that fluctuations, there is no strong bond. There is a weak bonding. That's why the bonding energy is very, very less. So fluctuating. So in the name itself, you have to identify fluctuating induced dipole bonds. So what is happening in generally, all atoms experience a constant vibration. In generally, all the atoms, they experience a constant vibration. Why means they will continuously run instantaneously. They will run symmetrically. So if you see in this figure, the figure A, okay, this is an electron cloud. This is an electron cloud, and this is the atomic nucleus. So what is happening? This is being circulating continuously like this in symmetric nature. In symmetric nature, it is being like this. It is being transferred. Now, what is happening during this motion? During this symmetric motion, the atom is experiencing some vibration because of the force of attraction. So because of this vibration, what is happening? There is a disturbance. There is a position disturbance of the atom. So if you see this figure, so this symmetry nature is changing to unsymmetry. So there is change in shape. Like this, it is being formed. If you see the B figure. So because of this unsymmetry, the position of that molecule. So earlier it is in exactly the center. Now it is going to somewhere corner. If you see the figure B. So now, how there will be a good bonding now? Now I'll show in the figure. So here you have exactly at the center. And if the other atom is also like this, there is strong bonding like this. If it is a symmetry in nature. But now in this example, what is happening? Now earlier it is symmetry. Now after some time, it is changing its symmetric nature like this. And the position also shifting somewhere like this. It is changing its position. Now, how can you get the bond? See, like this you have to get, but there is change. So, because of that change in position of the atom and change in the symmetric nature, okay, there is no strong bonding between the atoms. That's why you are getting a very, very weak in nature. So, this is one of the type where you are getting the secondary type of bonding, that is fluctuations. Because of the vibrations, the fluctuation, there is change in position of the atom, there is change in the symmetry in the nature. So, there is a disturbance in the position. So, the bonding between the atoms is not perfect. It is imperfect. That's why you are getting a weaker value. So, this is fluctuating induced dipole bonds. So, as we discussed, one of these dipoles can in turn produce some displacement. There is change in position from one position to another position. Because of that vibration in nature, there is a change in the displacement. So, because of the displacement, what is happening? The second type of bond from another atom is trying to attracting, but because of the change in position, it is unable to contact. It is unable to get good bonding between each. So, these attractive force, though the attractive force is existing, but there is a no strong between the atoms. So, this is how you can observe. So, this is the center position and this is change in position. So, the attractive force is changing. So, that's why you are getting less bonding value. So, this is one of the fluctuating induced bonding. So, these are all happening. The main characteristics is what? Dipole nature. Dipole nature means there is a distance. The distance between the two atoms is very, very high. That's why all this type of bonding is happening. And if you compare with the solidification and liquefaction time, there also you are getting very less values. When you compare with the primary values, the solidification values or the melting temperature values are very, very less. That's why these are not suitable in many applications. The materials which are having secondary bonding are not suitable for many applications or which are related to mechanical applications also. So, another category is what? Polar molecule induced dipole bond. So, wherever you see this dipole, that means there is a gap. There is a gap between the atoms. Because of the dipolic nature, you are not getting a good bonding between the atoms. So, second category is what? Polar molecular induced dipole bond. So, this is a permanent dipole moment which is existing between the two atoms or molecules by virtue of an unsymmetry arrangement. Again, these are having unsymmetric and symmetric arrangement, though it is a positive and negatively charged, but because of the permanent dipolic nature. Permanent dipolic nature means it is having a permanent distance. There is no change again. So, you have a permanent dipole moment is existing between the two molecules or the two atoms. So, there is a no good bonding in this type of bonding also. Though the positive and negative charges of atoms are available, this is not giving a good strong bonding. So, this is one of the polar molecule induced dipole. So, what is happening in this case? The polar molecule can also induce dipoles in adjacent non-coplanar molecules. So, again, though you have adjacent bonding in this type also, like covalent bond. In covalent bond also we have adjacent bonding between the atoms. Then you are getting a strong bond. But in this case also, though there is existing of adjacent bonding between the atoms, but since dipolic nature is present, you don't have a strong bonding when you compare with that covalent bonding. So again, you have a greater fluctuations are being induced in this dipolic nature. So because of this higher values of fluctuations, there is no strong bonding between the elements. The third category in the secondary bonding is what? Permanent dipole bonds. So this is also same. Van der Waals forces are existing between the two adjacent polar molecules. So two polar molecules which are being adjacent to each other, there you have van der Waals force of attraction, the positive and negative nature. Again, since there is a dipolic nature in this case also, there is a weakness in the bonding nature. And the strongest secondary bonding type, only the hydrogen is having a good strongest bonding nature in the second category of secondary bonding. The third one is permanent dipolic bonds. Now if you compare the values with the primary and the secondary bonding, now you can see easily, so these 1, 2, 3 comes under primary category, and these last two comes under secondary category. Okay, now you see the values of the bonding energies between the primary and secondary. See, all the values in primary are having very, very strong bonding energy, since the ionic nature, covalent nature and metallic nature. Because of these three natures, you have a strong bonding between the elements. But when you compare the secondary bondings with the primary, so you have very, very less values. See, you can see only 7.7, 31, 35. So these are very less values. So these are not suitable elements when you compare with the primary. The secondary are having very less because of the dipolic nature in the molecules. You have less values of bonding energy. In the same way, if you see the melting temperatures, you are having almost 3500, 3400, 1500 values of melting temperatures. So this can withstand, though you are giving high amount of heat to the element, it will resist to that heat. But if you give the same heat or 1500 or about 1000 degrees, it can't resist. You can see these values. It is having only negative values, minus 189, minus 101, minus 78. H2 is having 0. Okay, like this. So it is having very, very less melting point. So main cause is what? The dipoles. Because of the dipolic nature in the secondary type of bonding, you are having less amount of bonding energy as well as very, very less amount of melting temperature. So only the primary bonding type, that is whether it is ionic, covalent or metallic. So these type of substances are very, very useful when you compare with the secondary. And also in some elements, though the secondary bonding type is available, this is being neglected because of these negative values, very less values. These are being neglected. Only the primary are being considered. Though the secondary is available, but the secondary is being neglected, and only you can select the primary type of bonding. Okay, so this is about the interatomic bonding between the elements. So these are the references where you can find the information about the interatomic between the different types of elements, and what are the different types of interatomic bondings related to primary or secondary, and what are the different bonding energies, and what are the different melting temperatures between the elements. So if you know all these things, it is very easy for us to select a material to the required application, where the high amount of energy is required, where high amount of bonding is required, where high temperatures the body has to withstand. So because of all these characteristics, if you want to have any application, then it is very easy for us to select the material. So for us to know all these things, we have to study the interatomic between the atoms. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.